So round two of rational functions and how to graph them. We're going to go through the same first process, but in the second process, we're going to see a couple of new points. First of all, in this case, we have a degree of our numerator being one more than the degree of our denominator. And like I said yesterday, if that's the case, we get what's called a slant asymptote. So let's start talking about that. First of all, like I said, let's take the same steps we took before. Find x-intercept, set y equal to 0. Setting y equal to 0, we get 0 equals x squared minus x minus 2 factors into x minus 2 and x plus 1. So therefore we have values of 2 and negative 1 as our x-intercept. Y-intercept, we end up with 2/5. Vertical asymptote, we know we have x minus 5 equals 0, so that's 5. And now we're going to need to calculate a slant because our degree of the numerator is one more than the degree of the denominator. In order to do this, we're going to have to use long division. So if we go way back to Algebra 2 and take and divide x minus 5 into x squared minus x minus 2, we remember we say x times what equals x squared. Well, that's an x. Multiply this term by the binomial out in front, we get x squared minus 5x. And just like back in 4th grade, we subtract all that stuff out. This is now a positive, so I have 4x minus 2. So my remainder. X times what is 4x? Well, that's positive 4. And we have 4x minus 20. Now, even though there's a remainder, it really doesn't matter because what we're trying to do is find a slant asymptote. And a slant is just a line. So y equals x plus 4 is our slant asymptote. We're going to go over and graph this now. I'm going to label my intercepts and my asymptotes. I have a vertical asymptote of 5, so I'm going to go 1, 2, 3, 4, 5. Put that little dotted line down. Slant asymptote at y equals x plus 4, so I go up 1, 2, 3, 4. Rise 1 over 1, and I have this slanted asymptote here. Now, just like the horizontal asymptote, the slant asymptote describes end behavior as well. So it really only talks about what happens when x is very, very big positive and very, very big negative. Our graph can cross a slant anywhere in the middle. Let's take and now plot my intercepts. I have an intercept at 2 and negative 1 right around here. And I have a y-intercept at 2/5, so somewhere in here. Again, I think I can graph this whole function without plugging in any points because I know I have to go through these 3 points in black here, and then I approach my vertical asymptote, and then I approach my slant asymptote as I get further and further out to infinity. Notice on this right side there are no more x-intercepts, so I know I can't go from the top down to the bottom without crossing that x-axis. So I know my graph must reside up in this region here. Let's move on to that next example. Again, I have a degree of the numerator, one more than the degree of the denominator. I can find my x-intercepts. Setting equal to 0. Notice in this case though, x squared plus 3 is going to equal 0. If I set y equal to 0 and multiply by x plus 2, I know that x squared will never equal negative 3, so therefore there aren't any x-intercepts. My y-intercept is going to be 3/2. My vertical asymptote is going to be -2. And now I have to find my slant. Once again, have to divide top by the bottom. But notice I'm going to leave an open spot for my missing x variable. X times what is x squared? That's an x. I have an x squared plus 2x here. Going to subtract that. This 2x is now a negative plus 3. X times what is -2x? That's a -2. I've got enough for my slant asymptote. Let's go ahead and start to graph that once again. I have a y-intercept of 3/2. I have a vertical asymptote of -2. And I have a slant asymptote of x minus 2. So rise over run once again. Again, I think this is going to be easy to graph. I know I have to go through the point 3/2, which means I approach that vertical and that slant. Notice on the left side of the vertical asymptote, I'm not crossing the axis anywhere, so I can't come from top down to bottom without crossing that line. Therefore, my graph resides in the lower left-hand region. To the next example. Now, in order to get my x and y intercepts, I might have to do some factoring of the numerator. I'm going to do that right off the bat. I have 2x, x, 2 and 1, 1, both adding, over 2x plus 7. So in this case, I have x-intercepts when setting y equal to 0 of -1/2 and -2. I have a y-intercept setting x equal to 0 of 2/7. I have vertical asymptote of -7/2. And then for my slant, I'm going to do my long division again. (2x squared plus 5x plus 2). 2x times what is 2x squared? That's just an x. So I have a 2x squared plus 7x that I'm going to now subtract. (-2x plus 2). 2x times what is (-2x)? It's a -1. There's my slant. So, moving over once again, let's go ahead and graph. This is going to be similar to the last example, I think. I will plot my asymptotes. I said I had a vertical asymptote of -3.5. Somewhere splitting that difference here. I have a slant asymptote of x minus 1. Rise over run. Something of this nature. And then I have several intercepts. I have one at -1/2, -2, and y equals 2/7. Again, fairly easy graph. I've got to go through these 3 points and approach my asymptotes. To the left, no x-intercepts, thus down here. But what changed is I factored the numerator first to find my intercepts. So it appears that this graph, once again, is going to have a slant asymptote. I start by factoring my numerator, just because I get in the habit of doing that. And I notice when I do so, I get the following. I get x plus 2, x plus 3 over x plus 2. Now you're going to notice that when I take and look at that new view of the function, this was not in reduced form. If I were to reduce that, I get the following. Y equals x plus 3, which means this is going to look like a line. Now, does that mean this is a line? Kind of yes, kind of no. We're going to get our calculators opened up and take a look at what's going on. So here I've got my calculator set up and I've plugged in the function. Notice what I've done though. I've taken and put the numerator all in one parentheses, divided by the denominator in one parentheses. If you don't do that, you won't get the accurate graph. Now, if we take and graph this, sure enough, it appears it looks like a line. However, we're going to notice something when we look at the table. If I move over to the table by hitting second graph, I notice at -2, I get an error. Now, it's just such a coincidence that -2 happens to be the answer of this reduction if I were to set it equal to 0. And that's important. What essentially we've done is we've created a hole in our graph. Holes happen when we have reductions. And those reductions are typically of factors. So in this case, I reduced an x plus 2. Thus, at x equals -2, there is a hole. Now, in order to find the y value of that hole, I have to plug -2 into my remaining equation. My remaining equation in this case is x plus 3. So if I say -2 plus 3 is my y value, y ends up equaling 1. So what I have is I have a hole at -2, 1. We'll see how that plays out in a second. Let's finish this up and take a look at the graph. Since my x plus 2 is gone, I have no vertical asymptote. All right? And what's remaining is strictly a line. So I'm going to go up 3 and go up 1 and over 1. And I'm going to actually draw a line. Except, here's the deal. At -2 and 1, my graph doesn't exist. It has an open hole. So this is a point discontinuity. We talked about that the other day. And my graph looks exactly like a line. However, at that point, -2, 1, I get a hole in the graph. So that's a new concept of the day. There's no slant asymptote whatsoever, and there's no vertical asymptote because it reduced out. Let's move on to the next example. Looks like lots of factoring. Let's go ahead and do that. got a 2x and an x. I've got a 2 and a 3. And this looks like it's going to go negative and positive here. It's all going to be over. Let's see, this function goes to x squared plus x minus 6. So this will go to x plus 3, and x minus 2. In this case, you'll notice my reduction is of the x minus 2 terms, which means I have a whole at x equals 2, but I want to find my y value. So in order to find my y value, I'm going to plug the value of 2 into what's left in my remaining function. So I have 2 times 2 plus 3 over 2 times 2 plus 3. That gives me 7 over 10. And my whole is now at 2 and 7/10. So what's remaining in my graph? Well, it looks like what I have is I have a degree in the numerator of 1, and a degree in the denominator is actually 2, because this function that remains is 2x plus 3 over x squared plus 3x. So that tells me the following. I know I have a x-intercept of negative 3/2, a y-intercept that doesn't exist because when I set x equal to 0, I get an undefined term. I have a vertical asymptote, actually 2, setting the denominator equal to 0. Here's my denominator, x and x plus 3 of 0 and negative 3. And I actually have a horizontal as well, because the degree of my numerator is 1 less than the degree of the denominator. Therefore, y equals 0 is that value. So I'm going to go ahead and graph this. And I'm going to plot some asymptotes. I have vertical asymptote at x equals 0, which is y. There was no y-intercept. At x equals negative 3, there's another vertical asymptote and a horizontal asymptote at y equals 0. Now I also have an x-intercept of negative 3/2, which is right around here. Okay, this doesn't give me much to go by. However, I also know at 2 and 7/10 I have a whole. That's actually helpful because I know my graph's got to kind of go through this point but not really be that point. It's above the axis. I know there's no x-intercept over here, so I know that as I go to infinity, it approaches 0, and it approaches over here. The other two sides I really don't know much about. So what I'm going to have to do, again, is plug into my remaining function to figure out what's happening. I'm going to plug in to this function here, values to the left and to the right of negative 1/2. I'm also going to take and plug in a value to the left of this asymptote at negative 3. So I want to take a look at the following values. F of, let's go negative 1, f of negative 2, and f of negative 4 to see what this graph's going to look like. And I will plug all these into the remaining end of this equation over here. Plug in -1, I get a positive in my numerator. The denominator, I get a negative and a positive. Negative and positive multiplied to a negative divided by a positive equals a negative. So on this side, I get a negative value. Plug in a -2. My numerator goes negative. My denominator goes negative and positive. Negative times positive is a negative. Divided by a negative is a positive. So to the left of this point, moving up. When I plug in a -4, my numerator is a negative value. My denominator is a negative and a negative, resulting in a negative overall. Therefore, my graph's down here. All right, so today we've looked at holes and slant asymptotes. Questions for you to answer are right here. Do your best with that, and we'll go over it tomorrow. Thanks.